So here the next part of the discussion here is, if you go to the numericals in solid state, let us do few more models in solid state. That is, if you go to the first numerical, a compound forms hexagonal closed packed structure. What is the total number of voids in 0.5 moles of it, and how many of these are tetrahedral voids, and how many of these are tetrahedral voids? So if you go to the first one solution, go to the first one solution, that is, the compound is HCP, compound is equal to HCP, and he gave that that is, what is the total number of voids in 0.5 moles of it. 0.5 moles of it means, let us take it like this, because he is saying 0.5 moles number of voids, because he is asking number of voids in 0.5 moles of HCP, hexagonal closed pack structure. If it is asking 0.5 moles, how many voids will be there? So let us put it like this: 1 mole of HCP at STP contains, that is Avogadro's number of 6.023 into 10 to the power of 23, contains 6.023 into 10 to the power of 23 voids, say for example, because you know very well that 1 mole of any substance contains Avogadro's number of properties. So 1 mole of hexagonal closed packed structure, if you take at STP, it should definitely occupy 6.023 into 10 to the power of 23 voids. So the same step, if you take for 0.5 moles of HCP, therefore occupies how much? So this is going to become 0.5 into 6.023 into 10 to the power of 23. Roughly I am taking this as 0.5 into, I am ignoring 023 after the decimal, 10 to the power of 23, which is equal to 3.0 into 10 to the power of 23 voids are already present for 0.5 moles. That means in 0.5 moles, so therefore in 0.5 moles, how many number of voids are present means, that is 3.0 into 10 to the power of 23 voids are present. Now we are saying how many of these are tetrahedral voids, but you know very well that, but since, I'll put it in this way, but since number of tetrahedral voids is always equal to 2 into octahedral voids. So whatever the number of voids we got, it is because of the octahedral voids only. So in 0.5 moles, 3.0 into 10 to the power 23 voids, this belongs to octahedral voids. So therefore now what I am going to do is, now if you want to calculate the number of tetrahedral voids is equal to 2 into number of octahedral voids. So 2 into number of octahedral voids is 3.0 into, that is 10 to the power of 23 voids. If you take, tetrahedral voids are going to become equal to, this is going to become 6 into 0.5 means, it is 3 into 10 to the power of 23 voids. So this is going to become 6 into 10 to the power of 23 voids should be the answer. So therefore if you want to calculate the total number of octahedral voids plus tetrahedral voids together for 0.5 moles, for 0.5 moles is equal to, here you can take 3.0 into 10 to the power of 23 plus 6.0 into 10 to the power of 23, which is equal to, that is 9.0 into 10 to the power of 23 voids have been identified in the case of, that is, the HCP structure for 0.5 mole of its voids which are present in the hexagonal closed packed structure. So here if you look into this problem, here a compound is formed by two elements M and N, and the element N forms CCP, and atoms of M occupy 1/3 of the tetrahedral voids. What is the formula of the compound? What is the expected formula of the given compound? So how do you approach this problem? Actually what we are doing here is, the compound contains CCP means FCC. So here when you say CCP, CCP is nothing but cubic closed packed, or you can say FCC means face center cube, both are same, face center cube, both are same here. So if that is the case, is saying that there are two elements, one is M and one is N. So the element N forms CCP. If you take N forms N, if N is forming a CCP type of arrangement, means what do you mean by this? Let us apply the shortcut. CCP means the rank of the crystal, effective number of atoms present in the cubic closed packed or face centered cubic lattice. The effective number of atoms present is equal to 4. This effective number of atoms we can call it as rank of the crystal. This if Z is equal to 4 is the rank of the crystal, and it is also equivalent to number of octahedral voids. So I mean to say, always whenever you are trying to do the problems, whenever you know the crystal structure in the form of CCP or BCC or HCP, whatever is the crystal structure, based on the crystal structure you have to identify the rank of the crystal. Once you identify the rank of the crystal, that rank of the crystal automatically it is going to give us the number of octahedral voids. So here it is very clear that now N, the element N is trying to contribute the octahedral voids. Now he is saying that the atoms of M occupy 1/3 of the tetrahedral void. So he is saying that he is giving one more element, that is M. When M is occupying 1/3 of the tetrahedral voids. But you already know that, we already know that here for M, with respect to M, I'll put it in this way, with respect to M, number of tetrahedral voids, okay, M is contributing 1/3 of the tetrahedral voids, but because 1/3 of the tetrahedral voids means the tetrahedral voids are always equal to double the number of octahedral voids. So 1/3 into 2 into number of octahedral voids we already know, which is equal to 4. So this is going to become 8/3. So with respect to M it is 8/3, and with respect to N it is 4. So therefore here, that is M is to N is equal to 8/3 is to, that is N value is 4. So substitute here 4. So 4 means 8/3 is to 4/1. If I am going to take 4 1s are 4 2s are, then therefore the ratio is going to become here, that is M is to N is equal to 2:3. You can take this as this, you can take it as M to N3. M to N3 is the final ratio where we can take for calculating the formula of the compound. So what is the formula of the compound? Means it is M to N3. So here if you look into this problem, this is the third problem. Analysis shows that nickel oxide has the formula, that is Ni of 0.98 and oxygen of 1.00. What fraction of nickel exists as Ni2 plus and Ni3 plus? So here approach. How do you approach the problem? What is the approach involved? The approach is you have to first identify, that is calculate number of atoms in Ni2 plus and Ni3 plus. You have to calculate separately, because he is using the nickel in two different oxidation states. We are supposed to calculate the number of atoms present in Ni2 plus species and Ni3 plus species. We need to calculate that, we have to calculate. This is the approach of the problem. And what is the nature of the compound? This nature of the compound is Ni of 0.98 of oxygen 1.00 is nothing but it is an interstitial, or you can say non-stoichiometric compound. So that means it contains variable oxidation state. Non-stoichiometric compound, that means it is having the variable oxidation state. So therefore now what I can do here is, because here nickel is trying to exist in two states, one is Ni2 plus and in another case it is Ni3 plus. Out of 0.98 the mixture is 0.98. What is the composition of the nickel? Means it is 0.98. So with respect to Ni3 plus, out of 0.98 I will take it here as this as X, and here I am going to take for Ni2 plus I am going to take, that is 0.98 minus X. So but in the meantime, you know that, but in the meantime the valency of oxygen is always, that is minus 2, that is minus 2. Minus 2 is the, because it is valence should be given only with whole number. Actual valence is minus 2, so that minus 2 should be represented in the form of 2, and it has to be equated with the actual composition of the nickel in the two different oxidation states. So let us take it like this: nickel is plus 3 oxidation state, so x into plus 3 is 3x, x into plus 3 is 3x, and here that is plus 2 oxidation state of nickel. So this is 2 of 0.98 minus x must be equated with the valency of oxygen. So valency of oxygen is already 2. So this I can take it as, that is nothing but 3x plus 1.96 minus 2x is equal to 2. So this is going to become x plus 1.96 is equal to 2. So x is equal to 2 minus 1.96, x is equal to 0.04. So if x you got 0.04, then what is the relative number of atoms? What is the exact number of atoms present means? That is number of atoms in Ni3 plus. Number of atoms in Ni3 plus, if you take, that is for x. So therefore, because x value if it is 0.04, so 0.98 minus x for, if x is 0.04, then I'll put it in this way: 0.98 minus x is equal to 0.98 minus 0.04, so that is going to become 0.98 of 0.04. if I take, this is 4, this is 0.94. So therefore in the case of Ni3 plus, actually 0.04 divided by the total is 9.98 into 100. So this upon simplification approximately you get 4%, nearly 4% you are going to get. And similarly number of atoms in Ni2 plus is therefore in Ni2 plus is therefore, that is 0.94 divided by 0.98 into 100, approximately we are going to get nearly, that is 96%. So therefore Ni2 plus it is 96% and Ni3 plus it is 4% is the numerical. So here the next part of the discussion in solid state is, this is the topic which is under our discussion, that is probing the structure of solids, that is through X-ray crystallography, and that is derivation of the Bragg's equation, also obtaining an expression for the Bragg's equation. So first of all, before going to the Bragg's equation, you know very well that if you take a solid, that is structure of solid, because let us start our discussion with the structure of solid. When you say here according to the Bragg's equation and according to the X-ray crystallography, when you speak about the structure of solid, if you are going to the structure of solid, the solid is always crystalline in nature. It is crystalline, and it has individual layers. Actually, if you take these individual layers, separation, I'll put it in this way: separation of layers, individual layers. Separation of individual layers results in grating. That results in grating. And what is happening here is, because we are saying that all solids are crystalline, usually if you take a solid in the crystalline form, if you take a molecular crystalline solid, the best example of molecular crystalline solid is, that is sodium chloride. Now if you go to the sodium chloride, what we are able to understand is, if you go to the entire composition of the sodium chloride crystalline solid, which is also called as rock salt. So what is happening here is, it is something like this. Actually what is happening here is, like the sodium chloride, suppose if I am taking one Na plus ion, suppose if this is one sphere, this is another sphere, this is another sphere, another sphere like this. Suppose if I take some group of spheres like this, which they are spherical in shape. So what you are able to notice here is, what I can say is, this is Na plus, this is Cl minus, again this is Na plus, Cl minus, again Na plus, this is Cl minus, Na plus, Cl minus, and so on. So if that is the case, what is happening here is, suppose if I am taking, suppose different layers, if you are taking different layers like this is the first layer, this is the second layer, this is the third layer, so on and so forth. And when I am taking different layers, each position is occupied by certain number of spheres, 1 2 3 4 5 6 7 like this. Again one more sphere, if you take 1 2 3 4 5 6 and 7. So again here also 1 2 3 4 5 6 and 7. These are all individual layers. If you take, these are the individual layers. I will take this as the first layer, I will mark it as AB, second layer I will mark it as CD, and the last layer I am going to mark it as E and F. So each sphere, as already I told you, if you look into the continuity of the layers of the spheres, if you take, each sphere is made up of one atom, and one atom is carrying positive charge and the other atom is carrying negative charge. And you know very well that in a crystalline solids they have high melting point and boiling point, because the oppositely charged, the cationic species and the anionic species, the cationic spheres and the anionic spheres, because of the strong electrostatic force of attraction, they try to bind against each other very strongly. So large amount of energy is actually required to break the strong electrostatic force of attraction operating between the two oppositely charged spheres. So what is happening here is, from one layer to another layer, if now from here what I am doing here is, I am trying to pass, straight away what I am going to do is, I am going to pass one radiation, because here because the method is X-ray crystallography. If you take X-rays, if you are taking about X-ray, and X-ray is nothing but, it's a radiation. X-ray is a radiation source, radiation which is obtained from Coolidge tube. X-rays can be obtained from Coolidge tube, and these X-rays have certain calculated quantity of wavelength, and you know very well that X-rays have more energy and less wavelength compared to the ordinary light. So therefore these X-rays, some group of X-ray radiations from particular source from the Coolidge tube, if you are able to obtain X-rays, these X-rays, they try to come and strike the first layer of the crystalline solid like this. If they are coming and striking the first layer of the crystalline solid like this, this is the point of striking the first layer of the crystalline solid, then the angle made by it is theta, and let the radiation be represented by y. The moment it is striking the first layer at one particular point of the sphere, this radiation of the X-ray, this is incident radiation of the X-ray striking the first layer. So immediately this first layer gets that is reflected. So when it is reflected, it is going in the opposite direction, and again it is trying to create certain angle. In the meantime, there is one more X-ray radiation. Imagine that there is one more X-ray radiation, that is Z, coming from particular source. This is also an X-ray radiation. Z is another X-ray radiation originating from certain point, and it is striking the it will strike the first layer, and then from there it will go and it has to strike the second layer like this, and again from the first layer it has to move, again it has to get diffracted, and it has to get diffracted, it has to move, again it reflects back in the opposite direction. So therefore this is the angle of incidence, and this is again angle of reflection. So what is happening here is, you can find that here, that is here you can find that there is one particular point where that means the second X-ray radiation is traveling up to a distance of, this I will mark it as, this is the interplanar distance, this is the interplanar distance, this I will mark it as and I am going to extend the perpendicular also. Here also I am going to extend the perpendicular. So here I am going to take the theta value Here also I am going to take theta value, and here I will mark it as this, I will mark it as P, and this I will mark it as Q, and this is R, and this is S. So that means what is happening is the second X-ray radiation is coming and striking the first layer of the crystalline solid, and it is penetrating into the second layer. From there it is trying to again deflect. So this is the angle of incidence, and this is the angle of reflection for the second X-ray radiation. So from this observation it is very clear that the second X-ray radiation is traveling an extra distance of Q, R and S, is the extra distance which is travelled by the second X-ray radiation compared to the distance travelled by the first X-ray radiation. So from this, the property of triangles, you can see that there are two triangles obtained here. One is PQR, one right angle triangle, and another one is PRS is also one more right angle triangle. And here outright what I am going to do is the distance, the perpendicular which is drawn from P to R is nothing but the interplanar distance. I will mark this as, that is D. I will mark that as D. So here what I am going to do here is like D is the, so here I am going to take it like this, Y comma Z are the incident X-ray radiations in same phase striking the layers of crystalline solid striking the layers of crystalline solid between AB and, that is, C and D. AB and C and D. Here PR I can take interplanar distance. PR is the interplanar distance. PR is the interplanar distance between two layers. If PR is the interplanar distance between two layers, then what I can do here is I can take here one, I am going to take here something like, I want to create a right angle triangle like this, and I will start from here P, this is Q and this is R, and definitely here PR I am going to take it as, that is D. This is nothing but D. So here one thing what we have to understand here is, that is from this triangle I am picking up one of the right angle triangle I am trying to pick up from this diagram and from that illustration. The radiation, that is, if you take PR between the two layers, that is the interplanar distance between the two layers, it is the interplanar distance between the two layers, and the ray Z has to travel, a longer distance. The ray Z has to travel a longer distance of Q, R and S. It is travelling to a longer distance. If you are drawing a perpendicular from P, a point Q is observed. From Q it has to reach R, and from R it has to again one more perpendicular you are drawing from P to S. From here to here one distance it is covering, that is Q of R, and again R and S it is trying to cover another distance, that is R to S is another distance. So from here it will emerge out of the crystal. So therefore ray Z has to travel a longer distance which is equal to QRS in order to emerge out of the crystal, that is observed in the diagram. Then from there also what we have to understand is, after reflection the difference in distance travelled by the two rays must be always equal to the integral multiple of n into lambda, where n is the order of the that is crystal, order of crystal means whether a given crystal is following the first order, second order, third order. If n value is 1, that means the crystalline solid is going to become, it contains only one crystalline plane. If n is equal to 2, it contains two crystalline planes. N is equal to 3, again 3 crystalline planes, so on and so forth. So n represents the number of crystal planes observed in the crystalline solid, and it is also going to give the order of the crystalline solid. So therefore n is the order of the crystalline solid, and lambda is the wavelength of the X-ray radiation. So it has to be observed that after reflection the difference in distance travelled by two rays must be equal to the integral multiple of n into lambda. So difference between the two X-ray radiations is actually taken in terms of PQR. Why is saying PQR? because P to Q, if you are extending from P, if you are extending a perpendicular from P, it will join Q. So Q and Q to R, so P to Q, it is giving the distance, and Q to R and R to S is another additional distance. So here PQR is equal to PQ of R. PQ of R is equal to n lambda, integral multiple of n lambda. If PQR is equal to n lambda, then Q of R and R of S is also equal to P into R into sin theta. So if you select one of the right angle triangle, the PR is going to become the distance between the two. P to R is going to become, this P to R is going to become the distance between the two planes, and Q of R and P of Q. If you take Q of R, this Q of R, this is Q of R, and again R of S, this is R of S, Q of R and R of S. If you take, okay, R of S is going to the right side of the triangle, so no problem. Q of R is equal to R of S is equal to PR into sin theta. So PR sin theta, that's because sin theta is equal to, therefore now we can easily understand that it is adjacent by hypotenuse. So therefore QRS is equal to twice the PR of sin theta. Twice the PR of sin theta means, anyhow we know that PR is equal to distance, so in the place of PR we are substituting D, and from these three equations finally we get the expression that is for the Bragg's equation expression. So therefore find the final expression from these three equations. The final expression is going to become n lambda is therefore equal to n into lambda, the integral multiple of n into lambda, that is wavelength of the X-ray radiation, is equal to 2 into the interplanar distance d multiplied with sin theta. So therefore Bragg's equation is equal to, Bragg's equation is therefore finally derived as, Bragg's equation is, that is n lambda is equal to 2d sin theta, where here n represents the order of crystal planes, where n can occupy the value 1, 2, 3 and so on.